So at this point in our crash course of how the Earth isn't always just cold and the frozen depths of space, we've now introduced two ideas: the fact that there's this envelope of gases around the Earth that we call the atmosphere. Like I said, we're going to focus on the troposphere. That's our little zone. It's the boundary between the troposphere and the next layer is roughly 12 kilometers. Actually depends on where you are. So 7 miles. You can think about it. If you were to go up 7 miles, you'd cross out of the troposphere into the stratosphere. So now we've got the Earth here. Not a very good drawing. Makes sense to me. Hopefully it makes sense to you. And so we have this radiation coming into Earth, and it turns out we've got all these gases out here in the atmosphere, if you guys remember that. Well, when the radiation comes from the sun, it's really hot. It's shortwave radiation, so it's wiggling really quickly. And what happens is that shortwave radiation generally punches right through the atmosphere. It is true, some of it gets scattered off of clouds and some of it gets reflected back. Also, once it hits Earth, things get reflected back. We're going to explore the details of that later. We're just talking about big picture stuff here. It hits the Earth and the shortwave radiation comes in, it hits the Earth and it's absorbed into the Earth. Now, you're familiar with this again. This is every day, something that we deal with. So think about on a hot sunny day, the sun's beating down, and the pavement will heat up to the point where you can't walk on it with bare feet. It's not glowing red, but what you've seen is shortwave radiation that's very short wavelength. It comes in, is absorbed into that material, and that material begins emitting radiation, but it's in long wave radiation, like infrared. So if you think about, we've got a couple of cats on a late summer night, they're out laying on the concrete on our patio because it's still emitting long wave radiation. The Earth does that. So during the time when the sun is shining on a particular portion of Earth, it's absorbing radiation, but the Earth sends that same amount of radiation, but in the form of long wave back to space. Now, we can think about the balance, right? So if you have incoming radiation, some amount, and you have outgoing radiation, those two things have to be in balance, or the Earth would do one of two things, right? So if it were losing more radiation than it were getting, the Earth would start to cool and cool and cool and cool, and you could end up with something that, well, in my historical geology class, we talk about snowball Earth. If this were to be out of balance the other way, and there would be more radiation coming in and less going out, the Earth would get warmer and warmer and warmer, and you'd end up with something like Venus, where there's molten lead on the surface. But you would hope that the amount of incoming radiation and outcoming radiation was matched, and then that means the temperature on Earth wouldn't change. So in thinking about how that long wave radiation goes back out to space, it turns out the pathway, the exit that long wave radiation takes to get back out to space, that's kind of the throttle, if you were to think about it. If there was a situation like the moon, where there's no atmosphere, the radiation comes in during the day, blows right out at night, and the day-night differences might swing hundreds of degrees. In Venus, it comes in and it just stays trapped and gets hotter and hotter and hotter. And on Earth, some of it goes back out, but it goes out at kind of a slower rate. And that's because long-wave radiation has a hard time getting back through the atmosphere. It kind of slows it down. And that's fundamentally why we don't freeze to death every night, right? The fact that long-wave radiation is slowed down on its way going back to space. So where am I going with this? Well, we're going to go back to thinking about what's in the atmosphere. Nitrogen, oxygen, those are two molecules, that's what the little bubbles are. Argon, which doesn't care. And then this funky guy here, CO2. And so that long wave radiation, when it's trying to get back to space, this is what it's faced with. It has to get back through these molecules. And it turns out when that radiation hits something like nitrogen, molecules wiggle when they're hit with energy. Nitrogen doesn't wiggle very much. It actually can only wiggle back and forth. It has what we call 1 degree of movement. It's a bad dancer. It can't absorb very much radiation. The same is true for oxygen. Argon doesn't care. The radiation bounces right off of argon. But when that stuff hits CO2, CO2 can wiggle in each direction of bond, and then also in this kind of back and forth sense, right? So CO2 has 3 degrees of movement, meaning that long-wave radiation is wiggling in form of infrared radiation is coming through, and it hits CO2, and it actually is absorbed by CO2 and transferred into kinetic energy, and that CO2 starts wiggling around. So kinetic energy, kinetic means movement, and that CO2 molecule begins to wiggle. And as it's wiggling, it's actually producing or remitting that same energy in the form of heat. So CO2 is special because it absorbs energy and it also produces energy that's been absorbed. Just like the concrete in your yard that your cats are laying is emitting long-wave radiation. Okay, so what are we looking at now? So I drew, here's the Earth, here's space, and I've got all of these molecules drawn in just represented by dots. So we know that most of them are nitrogen, kind of 20% of them are oxygen, a little bit of them are argon, and CO2, which was special, it's currently at a concentration of about 425 ppm, parts per million. So if you took 1 million molecules of the troposphere, 425 of those would be CO2 molecules. So this long-wave radiation is working its way back out to space, but every once in a while it's running into these CO2 molecules, and those are absorbing that heat and radiating that heat out in this kind of spherical pattern, right? Because it's non-discriminate. That are holding on to that long-wave radiation and bouncing it back to Earth, which means the heat can't leave very quickly, and that's why every night we don't freeze to death, right? So if you think about, again, if we didn't have an atmosphere, if we didn't have these gases that function this way, when the heat was gone, it would just leak directly out to space. Here, it's like we put on a blanket, right? So we're not losing heat, we're trapping some of that heat, even though a blanket isn't going to trap 100. So in the summer, maybe it gets down to 70 degrees at night. And the reason why is because that long-wave radiation is getting trapped by these CO2 molecules, and those are bouncing that energy back down to Earth. It's why we don't die every night. It's the warm blanket that prevents us from freezing to a cold, terrible death, I guess, for lack of a better term. So that's kind of an interesting idea. Hopefully that made sense to you. That's all we're going to kind of get into with this stuff for now. But now what I hope that you came out of this with was remembering that the atmosphere is layered. We're concerned mostly with the troposphere, the mixing sphere, the weather. Radiation is emitted in shortwave radiation, is absorbed as long-wave radiation, or absorbed as shortwave but remitted as long, and that CO2 prevents that long-wave radiation from just blasting straight out into space. It kind of slows it down, and when it does slow it down, that means there's heat retained in the atmosphere itself. That's really fundamental to thinking about Earth's climate, right? That's why life is possible on Earth. The fact that there are gases in the atmosphere that can do this. Okay, I'll catch up with you guys in the next video. We'll see how it shakes out. All right, bye.